Hello, everyone. My name is Amin Totounferoush. I am a PhD candidate at the University of Stuttgart, an Institute for Parallel and Distributed Systems, together with Professor Miriam Schulte and our colleagues from German Aerospace Center, Neda Ibrahimipour and Zabiner Lohler. We present our work on a data-driven approach for intercode load balancing in partition multiphysics simulations. I will start with a short introduction, then I will introduce the proposed load balancing scheme. Then I will investigate the performance of the proposed scheme by presenting results for a numerical example, and at the end there will be a conclusion and summary. Okay, let me start directly with multiphysics problems. These series of investigations study the phenomena where more than one physics is involved. Here I have two examples. In the first examples, we see the blood flow inside the human aorta. There we have the, the blood flow, which is representative of fluid domain, and the aorta wall, which is kind of solid domain. And the second example is the simulation of fluid flow or airflow in this example around the aircraft wings. To investigate these kind of problems, there are generally two groups of methods: monolithic methods, where equations from old physics and scales are discretized and solved as a single large system. On the contrary, there is partition methods, where problem domain is decomposed into smaller subdomains according to occurring physics or the scale, and for each subdomain, an independent solver is used, and a coupling method is implemented for data communication between different solvers. We follow a partition method. There are very good reasons to follow such methods. The first reason is that these methods give greater robustness and flexibility for software development. We are able to use well-adapted and validated numerical methods for each subproblem by using a partitioned approach. Also, previously developed and optimized single physics solvers can be reused here. These together reduces the software development cost significantly. We have some challenges when we use these partitioned approaches. The first challenge is that we need parallel single physics solvers. If we want to have very efficient simulations, then the single physics solvers must be optimized at the first level. The second challenge is intercode data communication. The communication plays an important role in partition solvers because the boundary data must be exchanged between solvers, and efficient data communication is a key point here. Boundary data mapping is also an important issue because not all solvers use same mesh. Different meshes can be used by different solvers, and if those meshes are not matching, then we need kind of mapping the data between different solvers. The equation coupling for strongly coupled simulations, where we have to use iterative procedure for each time step. Without an acceleration scheme, the iterations can take forever. So this is also a very important issue. And finally, the intercode load balancing, which I'm addressing in this presentation. This is different issue from what we know from classical solvers inside a single physics solver. This says basically that if you have, for example, 10,000 CPU cores and you have two solvers, how you should divide these cores between your solvers. That minimizes the idle time and maximizes the efficiency. In this presentation, I'm gonna introduce a data-driven approach to address this issue. Okay, our goal is to design and implement an efficient core distribution scheme between solvers to minimize the waiting time. As I explained, in a partition simulation, available compute resources, here means CPU cores or GPU cores, should be distributed among coupled solvers. You have 2 or 3 single physics solvers, and you have, I don't know, 10,000 cores. You need to kind of distribute these cores between your solvers. For partition simulations, solvers typically exchange boundary data at the end of each time step and iteration. or iteration. This means that every solver cannot continue until it receives the boundary data from other solvers. This means that if one solver is slower than other, the faster solver will have to wait until the slower solver finishes its work and sends the data. This can kill the performance of the coupled framework if the distribution of cores and load balancing is not ideal. Therefore, I introduce a data-driven approach to address this issue. The proposed scheme consists of 2 steps. At the first step, we should model the performance each solver. But for this, we gather some performance data from small simulations, and then we use performance models, and by optimizing this performance models and choosing the best model, we select a good performance model for each solver. After finding good performance models for each solver, we can incorporate these models into an optimization problem to calculate the optimal core distributions between different solvers. Okay, for performance modeling, we use a PMNF performance model norm form. Regression, we just you use the method from the paper that I cited here in this slide. This regression suggests that we use such formulation for modeling performance of the of each solver. Here, F is the runtime of the solver, and P is the number of cores that we use. We can use different terms for the performance modeling. Here, as I explained, F is the solver runtime, P is the number of processes, N is the number of approximation terms, CK is the weight for each term, and IK and JK are empirical coefficients. For N and IK and JK, we can use this space. How we choose a good model is that we check all the combinations of N, IK, and JK, and just pick the model with the lowest error on a validation data set. Okay, after finding the accurate performance model for each solver, we define our optimization problem. Here we want to minimize the capital F. The capital F stands for the total runtime, which is function of a core distribution between solvers and other parameters. And we have one condition here that the sum of all cores assigned to all solvers should be smaller than the available number of CPU cores. This is an obvious condition that we have here. Okay, how to interpret this optimization problem depends on the code execution scheme. The code execution can be serial or parallel. In a serial execution of coupled codes, one solver runs and sends this data to the other solver, and the other solver receives the data and do its computation and just sends data back. This can be explicit, where there is no iteration for each time step, or it can be implicit, where we have to iterate until the simulation converges. So for serial execution, we should minimize the sum of runtimes of the involved solvers. Here, F1 plus F2 is what we should minimize. On the other hand, if we execute the codes in a parallel fashion, then both solvers run at the same time, and at the end of the iteration, they exchange data. This also can be serial, it can be explicit, where no iterative procedure is taken, or it can be implicit, means that we have to iterate the simulation at each time step until it converges. So in this case, the F is defined as the maximum of F1 and F2. Basically, it means that we should minimize the waiting time of one solver. This means that the different solvers should have as close as possible the runtimes to each other. Okay, now after defining the optimization problem, let's see how we can solve the problem. The point is, Fi's are not generally monolithically decreasing. This means that we can increase number of cores, but the runtime of the solver can increase if it is outside the scalability region. In this case, where it's not monolithically decreasing, the optimization problem can be nonlinear, possibly non-convex integer optimization problem. If we limit the number of cores to the scaling range, then we can assume that by increasing number of cores, if i's are decreasing, so we can assume that if i's are monolithically decreasing. So with this assumption or with this limitation, we can simplify our constraint to this. This means that we can use all our cores. We increase number of cores, and the simulation time of each solver reduces. And by this, the optimization problem can be solved by brute forcing all possible assignments for PIs. This is relatively cheap because, for example, if we have 1,000 nodes available for our total simulation on SuperMUC, this means 48,000 CPU cores. This is only 999 combinations if we have only 2 solvers. So this can be calculated relatively cheap. Okay, let's have a look at a numerical example. I showcase performance of simulation of fluid flow around an aircraft wing. We divide the total domain into 3 subdomains: inner domain, middle domain, and outer domain. And for each domain, we use an independent instance of Attila solver, which is a discontinuous Galerkin solver. And we use precise coupling library for data communication, data mapping, and equation coupling at the boundaries. Okay, for inner domain, we solve Navier-Stokes equations. Our computational mesh has around 4 million degrees of freedom. For the middle domain, we use only Euler equation. Our degrees of freedom are more. We have around 8 or 9 million degrees of freedom. And for outer domain, we use linearized form of Euler equation, which also has around 4 million degrees of freedom. For data communication between solvers, we use fully point-to-point communication via TCP/IP sockets. And for data mapping, we use nearest projection method. Okay, let's have a look at the results. First, I show you the performance of the performance modeling. Here, I show the performance of each solver, the inner domain, outer domain, and middle domain. Okay, here I showcase the load imbalance between different subdomains. With this definition, I show that up to 5,000 CPU cores, almost we have less than 2% of load imbalance. For a smaller core number, we see a larger load imbalance. This is because in the smaller nodes, the distribution is not really fine because we cannot share a node between different solvers. So this is really a machine limitation, not the method's shortcoming. Okay, let's have a look at the scalability. Here, by increasing number of cores, we see that the runtime reduces nicely. Here, the blue graph is the case without load balancing, and the black graph is with the database load balancing that I explained. We see almost 20% runtime reduction due to better load balancing. Okay, in conclusion, I have introduced a data-driven approach for load balancing between different solvers in the partitioned approach. The method is able to accurately predict the solver's performance and also distribute the loads ideally between different solvers, and it reduces the runtime by 20%, and load balancing is less than 2%. After here, we have ignored the communication cost because for the example I explained, the communication cost is low, but for a communication intensive application, we have to consider the communication cost, for which we need multi-parameter modeling. Currently, neural networks are being investigated for this purpose. So with this, I would like to thank you for your attention